So a big round of applause for Mihai.
Okay, thank you. So the talk today is a little bit of an experiment that we started. Everyone was kind of jumping on this AI topic. I think that one. And we wanted to also experiment with it to see what we could do out of it, what we could find it useful for. So just as a little bit of a background, at Orange we're building an open source project which is called the Sylva project. It's basically a sort of a way to deploy a Kubernetes cluster as a service, let's say. We are trying to be a bit agnostic of various platforms, so you can use infrastructure such as bare metal, OpenStack, VMware, or OpenNebula as the infrastructure on top of which you can deploy all of these. As operating systems, we support deploying with either Ubuntu or OpenSUSE. And as a Kubernetes flavor, this is a bit, let's say, I should have updated the slides a bit, because we support RCA2, kubeadm, canonical Kubernetes, and OpenShift as Kubernetes distributions. And on top of it, we come and install a lot of basically tools and other software stacks that we need to basically have the entire lifecycle management assured with Sylva. We use Flux to deploy everything in a GitOps way. We use the Cluster API to orchestrate and deploy all of these. We do hardware management, we do dependency maps and several other things that we need for the lifecycle management. So we've started creating a few basic AI tools, which would be, let's say you have your own Sylva deployment, you have maybe your own set of AI tools that you're already using, and you also would have this is sort of, let's say, proprietary way for now at least, some AI tooling around the Sylva downstream product inside Orange. The idea is still to be able to come with your own tools on top of it, being an open source project at its core, and be able to manage all of this, regardless of whatever we provide or not. We've started simply with the Sylva stack tools for AI. We had some issues with focusing on several Sylva concept itself or Sylva CRDs that we're using inside the cluster. We needed to format all the requests and everything that we passed through there in a YAML format, because it would be at least what some of the studies are saying, that the LLMs understand better if you give it a YAML structure, and it also helps you to kind of give it some safeguards over how the output will look in the end. So we started initially with a RAG, because that seemed to be like the obvious choice for a big project, to have all the devs that are focusing on technical features and merge requests and everything like that, have all that information put inside the RAG that newcomers or juniors can, or even seniors can easily look into or ask questions about it and so on. People don't really write documentation as it should. I'm sure everyone is very well aware of it. Or sometimes it's just difficult for people to find the right MR or so, because what we've discovered is that a lot of the best documentation that we've written is actually inside the merge request itself, because there you have people that are reviewing it and asking a lot of information. So a lot of the things that are very interesting or the niche cases are actually inside the commentaries themselves of the MR, and nobody really bothers to put them later on in the official documentation page. This was actually an example of such case, because for the Sylva unit operator upgrade, you couldn't find any kind of documentation anywhere except for this MR alone. So you had to actually ask about around the team to see who will know about this, and then you'd get point to this guy that created the MR initially, and he will tell you, you know, this is working like this because such and such. So what were the choices basically? We could ask the devs to write more documentation, which we know is going to happen, but it's going to always be maybe half-assed. Or we can let AI write the entire documentation, which is going to get done, but it might be more half-assed. So we wanted to do it kind of put your hands together and have this merged stuff. What we ended up doing it was actually initially scrape the entire MRs that we had on Sylva-Core project, which is available on gitlab.com. It's a public project. With all the comments, with all the issues, with everything that we had, we gave it a sort of a rating system in which a comment from one of the maintainers of the project would have a higher value than the one of just a regular contributor. So, you know, it kind of comes with a bit of weight on the maintainer's shoulder, you know, to that whatever you put in there is going to have to be treated with a larger weight than what everyone else is saying. But the idea was that it still wasn't really quite enough. I mean, okay, we built a RAG, but how is this really actually helping us, aside from a few guys that are joining the team now and then? So, of course, there are some issues with this. If you are going to take this RAG and give it out to all the people that are using Sylva-Core, a lot of GDPR issues, because maybe I put a comment in there that I might not like it, or maybe it was 11 in the evening and I said something worse, and then that gets packed into the RAG and the LLM will spit it out to someone asking a questions later on. But we still didn't have enough to actually change some things into how operational teams are managing the clusters and so on. Because usually what happens in operation management, you may be flooded with tickets, you may be flooded with deployments and so on. Nobody is actually maybe taking all the times to put everything that they did everywhere, to specify certain issues and so on. And we thought about having a sort of root cause analysis system that would take care and keep that in mind of all the investigations that were ever done. So this is kind of how this started our entire work on this. Of course, why we started it was a bit of curiosity, a bit of boredom, and of course the hype, because everyone was doing stuff with AI and we weren't. Just out of the bat, we do not think that this should be a way to, or seen as a way to replace operational teams. AI should still be kind of lurking in the shadows of our infrastructure and of our clusters, enhancing what people can do and helping them. So in the end, we want actually an AI-enhanced operations. We do not want AI-centric products. We started from the daily reality that we had with hundreds of alerts from Kubernetes clusters with multiple monitoring tools screaming, with netter function and infrastructure components that are failing, and with probably someone who's on call at 3 a.m. and trying to remember, you know, what kubectl flux or whatever command he has to do in this order to try to fix everything. The problem is that the mean time response is measured in hours usually. When you get called at 2 a.m., it's going to take a while until you actually start doing stuff. There is some sort of knowledge being trapped into some people, individuals that might leave the team and so on, and that knowledge is gone with them. And you also get a sort of burnout or actually boredom from doing all the repetitive incidents time and time again. So we started easily with LM Studio on a laptop with a kind cluster and Kubernetes MCP. We used packet flow as a framework to create the agent. We initially went to LangGraph. It turned out to be very complicated in itself for what we needed to achieve. I'm sure there are use cases for it. Don't hate me for this. This is actually from the Pocket Flow repo itself, because you might need everything that LangGraph is actually giving you and offering you, but you don't really need it at all times. So it's better to go with the easiest solution. Pocket Flow, it's actually a framework that only has 100 lines of Python. So you can easily go around that and add your own functionality and so on. And also because it's an open source project, we didn't want to get caught in any of the vendor lock-in or something like that. We wanted to keep it as open as possible. So Monbot is actually aiming to be this AA-powered incident response agent for Kubernetes and OpenStack infrastructure. Of course, adding things on top of it with time, like for a bare metal MCP and so on. It was actually built to maybe help operational people automatically triage some of those Prometheus or Grafana and do a full root cause analysis for it. So what you usually had before is you got an alert, you check the dashboard, you correlate some logs, check the metrics, do some kubectl, OpenStack commands and so on, look into the docs, ask that one teammate who you know it worked on this previously, and then eventually maybe find the root cause. What we thought about it is that you still receive an alert, but the AI calls some tools. It does some correlation with previous incidents and how it investigated. It provides a root cause analysis for you. It learns for the next time. It stores everything, and then you get to sleep a bit more, hopefully. Ha. Okay. Come on. Okay. So the stack itself, the entire agent was written in Python. It uses a think, action, observe kind of way. It's a bit similar to what you could call a Ralph loop, that it's being really the buzzword right now with Cloud Code and the other coding agents. We're using some MCPs for it, like KTS, Flux, Grafana, memgraph, Sylva, that we've built ourselves, and the GitLab one, so you can actually go, the agent can go and look at the issues or the MR or everything like that live on GitLab. We're using a memgraph for the topology to get it stored. We use RabbitMQ as an alert ingesting queue because we basically do not want that an alert is being sent and the agent is, I don't know, down for some reason, and then you lose that alert forever. It just gets stored in the RabbitMQ until it gets acknowledged, and it only does that after the investigation continues. We use, of course, Sylva-Core, and we used Slack as an output notification system so everybody can see what's happening. We've thought about it to be very plug and play, so it should be very easy if you would take this to just, if you have your own MCP for something, you don't have to modify the code, you just modify a .env file and say, you know, there's this new MCP here, go use it. We used as models Qwen3, Claude Sonnet, GPT-OSS, and O4 and O4 Mini. No need to say that Claude kind of won this one. But from the open source versions, Qwen was the obvious winner between it and the GPT models that are open source. Qwen is much better at this. So going a bit into the agents themselves, this basically, it's one agent, but it has 4 nodes, let's say. You have a think node, which initially received the alert. So it decides on the summary of the alert and the quick query in the memory to see, you know, did we treated this in the past? Is it something worth analyzing or not? And it has two outputs. It either does an action on it and investigates, or it sends it to the end node if the alert is already has already been investigated and known. If it's an action, it goes to the action node, which is the one that has access to a certain kind of MCP tools, which would be to run Flux commands, kubectl commands, OpenStack commands, and so on. It takes all that output from there and pass it to the observe node, which has a reasoning mode enabled. It will look at all those informations. It will check Grafana's Prometheus. It will check logs inside Loki itself. It will search for all those things and patterns on the metrics. And it will forward all this information together back to the think node. The think node will say then, okay, I either have enough information to conclude on a root cause for this, or I'm going to need to ask them for extra informations on the other nodes. And it does this in a loop until it satisfies the think node. At the end, it just stores the memory of not only the alert, but the investigation, the root cause, everything that it touched in a sense of Kubernetes resources or infrastructure resources. It sends the notification to Slack and then acknowledges the messages in RabbitMQ. This is a much better way to actually see it because it goes from Grafana Alert Manager to the webhook, RabbitMQ. It's a small parser there to kind of get rid of all the noise in the JSON or YAML that comes from Grafana. and then it does all that crazy loop until it actually gets an output. The iteration is going like something like where the think node is saying, oh, you know, we have these target deployments that are failing, so on and so forth, and it kind of gives a next focus or areas to focus on for the action node. It will look at all those things. The action node will run commands related to what it has been given to it. It will go to observe. It will check all those logs, like I said, and then it will basically do the final summary of what happened. This is actually there are actually some screenshots from mgraph itself. This is how it looked initially. We didn't have a lot. It was basically just the alert, the investigation, and if you're lucky, like something of a pod resembling like core DNS in there. It looked like a good start, but it was clearly not very useful when you're doing like deep troubleshooting inside of a very multi-node and with a lot of pods and namespaces Kubernetes architecture. So we stepped it up a bit. We actually created some parsecs that from each tool call that the agent does, let's say a kubectl get namespaces, all those namespaces in there are taken and are written in memgraph, and all the custom resources and all the OpenStack nodes and everything like that, and it will make the relationship between each and every one of them. So if you get an alert of, I don't know, CPU or memory or whatever in one pod in, I don't know, core DNS, and then you get a second one in, I don't know, keycloak namespace or something like that, the agent will go to memgraph, it will do a query and can actually relate, you know, across namespaces, across nodes, that this kind of issue has happened in there, even if it's not really the alert right now in the namespace that you have it. It will say, you know what, you seem to be having these kinds of issues in several namespaces. Maybe you should take a look at this because this is not an isolated situation that you're having. So, having a larger database for the past incidents, the resolutions in Quadrant, which was before, I just removed it, so it's not in there anymore because memgraph kind of took over it. It was easier to make these kinds of connection, and we actually started to get some really interesting messages from the LLM, like, you know, identical alert patterns across 4 attempts or across 6 namespaces or something like that. So one thing that also helped us was having a Grafana MCP, which is actually created by the guys at Grafana Labs. And it gives you instant access to all the data sources, which were most interesting in our cases were Loki and Prometheus. So you could actually have the LLM not just get the logs of a pod at that certain time, it could actually query the entire Loki database over whatever time frame it thought it could find an answer to. And as well as the Prometheus, it kind of started to look at the entire timelines and see, oh, the CPU actually only spiked for about 5 minutes, 2 hours ago, and then it was okay, and so forth. What we've seen as more MCPs got added, because like I said, initially was just Kubernetes one, is that it sort of switched from just checking what's running at that time in the cluster, and also started to look a lot in Grafana at the metrics level and basically the trends and statistics and everything like that. So it switched from having the primary data source, the Kubernetes API, to Prometheus. It switched the log retrieval from direct pods to centralized Loki. The knowledge base was in the beginning minimal, just the RAG. Now the knowledge base was comprised of the entire memgraph and the entire, like, I don't know, 500, 1,000 past investigations. It's changed the strategy a bit. It's first started to look at metrics and so on. And we've seen the tool going down for describe pod usage and stuff like that, because it was able to use Loki and other things. As a small, I don't know, note here, do we think that AI can replace ops, or it should? And the answer is quite a quick one, and it's no, but it can sure help a lot. It investigates faster than humans, especially at 3 a.m. when you had some few beers. it never forgets past incidents. It consistently checks the same resources and tells you when alerts are nonsense. And this is based on actually creating and mocking some kind of alerts in namespaces that didn't exist, or just sending a Grafana test alert and it wouldn't waste time on it. So it's, in the end, it's not a copilot, it's an autopilot that you could use. Or it's a copilot, it's not an autopilot. Sorry. Freudian slip. What we got was also some what the fuck moments from it, because at least until you kind of get all the prompts into place and kind of start to shaping it nice and slowly. Especially it's an issue when you change models a lot, because you're used to one model kind of responding well to a prompt, and then you switch to another model which has some totally different kind of issues and understand things differently. But we had things like it tried to get the low-key data source ID a lot, and it failed even more, because it just tried to, it basically took the Prometheus one and put an L instead of the P, because it said, oh, it's low-key, it should be with an L. It just tried with a tool name directly, and my favorite is the last one where it just says, data source. Go figure it. You should know. There's a graveyard of fail commands, which it tried to invent a lot of tools at some point. It says run shell command, whatever that might be. List PVC, run kubectl, run OpenStack. This is, although it happened only once for me, it was the nicest one ever. But then I started to think that maybe it's not that it's hallucinating, maybe it's just looking for things that it would need to get the job done. Because how can you actually investigate some things about Helm releases or PVCs or Flux if you don't actually have those tools at your disposal? There were some other things that were less nice when it tried to create pods and just wouldn't take no for an answer. So it tried to run the shell command, it couldn't. After 14 times, it realized that, I have to switch approach. And then it tried with privileged true, which didn't work either, but at least he tried. In the end, we have some examples, let's say, of how an actual output comes out of the entire, analysis. So you get an alert. It says that Flux Helm release is failing. It tells you the namespace, the pod, blah, blah, blah. This is just basic parsing, not a lot to do with AI. But then it kind of goes deeper into it, and it's saying, you're missing a root dependency in the Helm release in that namespace. This is cascading because none of the other resources can reconcile because of it, because they're waiting for it. And it just sort of goes and tells you also what you can start to have a look at. The same in this place, it just started at the replica mismatch, and it said, okay, one of the pod might be down, but looking into it, it was actually being scaled on, because someone wanted to, me. I needed to trigger some alerts. Sometimes the hardest part in this was to actually trigger meaningful alerts that the AI can actually investigate, because you don't usually have a lot in a dev environment, so you kind of have to create your own issues to start to. And that's pretty much it, actually. Went faster than I thought.